Hello, everyone. This is me making sure my microphone works. Does my microphone work? Hooray. Well, welcome, everyone. I am so happy to have you all here on this somewhat smoky night, but we are enjoying our filtered air and HVAC indoors. Now, before we get started with our event this evening, I want to remind you all that we have another amazing event coming up this Wednesday, July 22nd from 6 to 8 p.m. in the Sculpture Garden right upstairs. We will be hosting Sailgating. That is a concert with the two greats of Maritime Great Lakes folk music, Lee Murdoch and Tom Castle. They very rarely play a set, they very rarely play a concert together. So it will be a particularly great show for everybody. That is, again, free. It is a suggested donation only, but the ticket price, free. So I do hope we see all of you Wednesday for Sailgating. But without further ado, I have two lovely people here to introduce to you tonight. Jillian King Cargyle, yes, is a science communicator at Argonne National Lab. Outside of the lab, she writes children's books and articles for all ages to learn about the world around them. She will be moderating and presenting with Scott Collis, an atmospheric scientist and the head of the Geospatial Computing, Innovations, and Sensing Department at the Environmental Science Division at the U.S. Department of Energy's Argonne National Labs. He is also joint faculty at the University of Illinois. His research is at the intersection of data informatics, edge computing, atmospheric science, and radar meteorology. He uses and develops open source tools to extract geophysical insight from remotely sensed data at scale, which enables a deeper understanding of atmospheric phenomenon essential for the development of next generation meteorological models. And I learned just this evening, before we all sit down, he's also a diver. He has scuba dived on wrecks, but unfortunately saltwater only. So our underwater archaeologists will have to hook you up, right? But without further ado, Jillian, come on up.
All right, thank you so much. Thank you for having us here. So this talk is called Lake Effect Science, but we're going to talk a little bit about AI. So how many of you are AI users? How many of you have used ChatGPT or something like that? All right, maybe like half of you. Okay, good to know. We'll keep that in mind. How many of you have heard of Argonne National Lab? Oh, good. Has anyone been there? How many of you have been there? Awesome. Okay, we've got Argonne heads following us around. That's good to know. So for those of you who aren't familiar with it, Argonne was established in 1946 as part of the Atoms for Peace program. So we had unlocked this new form of energy and we were looking for ways to have peaceful, positive applications of it. So the national labs were born. Argonne is one of 17 national labs across the country. And we have a sister lab here in Northern Illinois that is Fermilab. They're also good. Fermilab's great, but we do all the science. We're very excited about that. We have several cutting edge facilities. Scott is going to talk to you more about the Atmospheric Radiation and Measurement Observatory, ARM. I'm going to tell you just a little bit about the Argonne Leadership Computing Facility because I like to brag about it. We have one of the fastest computers in the world. It is called Aurora, and it is capable of a quintillion calculations per second. A billion calculations per second. Yes. So as we talk about AI and we think about things that are enabling AI, Aurora supercomputer right down the road in Lamont is one of those machines that make it possible. But I will emphasize throughout the day that we're not just making like cat memes and things. We are doing science to save the world. So all of the AI we do is part of the Department of Energy's Genesis mission, which is a collaborated effort across the national labs to improve science outputs and improve our nation through artificial intelligence for science. So how many of you, you said you used AI, but how many of you know how AI works? And you don't have to raise your hands. Maybe some, okay, a couple of you like, is magic in the computer? Is that what we're going with? So AI, when we think about AI, we can think about, really, it's a lot of math, which is less exciting than magic in the computer. But tonight, you are going to get to be the AI. So when we think of large language models, something like ChatGPT is trained, it learns from something like everything on the internet. Okay, so it gets all of the text that people have written, all of the conversations that people have had, social media, good or bad, everything goes into it. So that might be great for those cat memes. It might not be good for science. So, but how does it work? So the LLM is going to read your prompt and you are going to help me be the LLM. It's going to generate words for us. So we're going to write one sentence. Our prompt is, or what we want it to do, is write one sentence about a cat sneaking up on its prey. So the is our first word. What do you think is going to come next?
Cat.
Hungry. Oh, it's hungry. Hungry what? Cat. Now there you go. Okay, so did everybody say cat? Pretty much everybody was a cat person here. So 80% was the likelihood that that would be cat based on everything this large language model has seen. Some might say kitten, feline, if you're fancy. But it goes with cat because that's the most likely answer. So it's quietly what? What's our verb? Lurks, stalks. Oh, okay. Hunts. Okay, crept. So this was a little less certain. So we didn't have everybody yelling cat, right? We had crept, stalked, moved, tiptoed were most likely. Okay, so we're gonna pick crept because that was the most likely answer. Toward the sleeping what? What is it? What is it? Mouse, rat, human? How big is the cat? Yeah, this is it's a tiger. It's a big cat. Okay, so maybe, so we didn't have that context. So maybe it was a tiger and it's a man-eating tiger. We didn't fill that in at the beginning, but mouse, bird, rabbit, hamster. You got a, so it's going to pick mouse. So all of that it's doing is it's predicting the next word based on the likelihood that it is seen. So it's using those probabilities, it's assigning a weight to those words, and then it's using that math to predict the next thing. But it doesn't know what cats are. It doesn't know what rats are. It doesn't know what creeping is. It's just like a very sophisticated Mad Libs. So, all right, I have another thing that we're going to do that needs some interaction. So who would like to play along and train a machine? You look like you're up for a good time. All right, let's draw. So another type of AI, how many of you have heard of machine learning? Okay, so some of you. Yeah, so machine learning, and Scott's going to talk a little bit more about this, it's something that is going to, instead of taking all that text, it might take other things, it might take millions of pictures worth of information, and it's going to gather information from that. So let's do some training of a neural network. Okay, so this is quick draw. So you got to come up here and do it. And so for you folks at home, we are on this drawing app called Quick Draw with google.com. So you could play along if you wanted to. Okay, so you're going to hit got it. And you're supposed to draw a church in under 20 seconds. All right. Yeah, just.
Bear with me.
And you can't hear it very well, but the saying, I see line.
I'm using the
Oh, we can't see it up there. Oh, no. Ooh, is there a way to flip it or? Okay. Okay. Well.
tried. It was terrible. I was using the yeah.
So, well, you can say it was anything.
I mean, it was the greatest thing. It's like the Sistine Chapel.
It was the most beautiful picture of a church I've ever seen. Oh, yeah, we could do it like that. But, well, the point, well, thank you. You did a great job. That was, you really missed out, everybody. That was, That was the best drawing of a church. This man is clearly an artist. But basically, you can play with that at home. What it's doing. Did I get it to the right spot? No, not yet. Geez. Oh, geez, Louise. Go back to Teams, go back to this, go back to here.
We'll just hit the, yeah, that did it. Should have done it.
That
did it.
All right, everybody with us? All right. See, I'm the science communicator. I'm not the scientist. So that's why they don't let me mess with the supercomputer. I'd be like, oh, geez, Louise, what happened? Are we still doing science? Okay. So, but what that amazing picture of the church was doing, it was training that model and helping you see how that worked. So you can play along at home with this slide, quick draw. If you want to try it at home, you'll realize that it's amazing and it was a very good demo. Thank you. All right. So now I'm going to bring up Scott Collis. Yes. Oh, no.
Okay, let me try to reshare. Sorry, everyone. Bear with us for a moment here.
Oh.
Did that do it? Okay. Hi, everyone at home. You're seeing me again. Hooray.
Right. Is it working now?
Yes, the at-home screen, Jim?
At home can see everyone. Oh, hey, great. All right. Well, Scott is going to tell you about his science, and then we're going to talk about a lot of different things.
Awesome source. Thank you so much, Jillian. Thank you so much for having me tonight. This is such an amazing space. My name is Scott Collis. I am an atmospheric scientist with a whole bunch of really silly affiliations that you see up there on the screen. I lead a small team at the Geospatial Computing Innovations and Sensing Group. We're a group of about 13. We really specialize in using mathematical techniques to understand our planet, whether that be cultural heritage, whether that be the way thunderstorms interact with global circulations and weather patterns in Darwin, Australia, or whether it be the way that extreme precipitation systems can uniquely impact communities here in Chicago. I also lead a small observational site out in our patch of prairie at Argonne. It's called the Argonne Testbed for Multi-Scale Observational Science. Also lead artificial intelligence with the Atmospheric Radiation Measurement User Facility. Jillian pointed out what ARM was just before. In the United States Department of Energy, we're privileged to have a series of user facilities. Those who know Argonne might know the Advanced Photon Source, or APS. You might know Aurora, our Argonne Leadership Computing Facilities. ARM is unique. I call it a unicorn because we actually have 9 national laboratories, including Argonne Pacific Northwest National Lab, Brookhaven, and a bunch of others that have come together to build a networked group of observatories across the world to understand how our planet works. Our flagship facility is down in Lamont in North Oklahoma. We have a site in the Azores at Graciosa Island, called our Eastern North Atlantic site. We also have a site in the northernmost point in these United States of America at Utqiagvik or Barrow, which is, from a maritime point of view, is fascinating with all the whale bones and the canoes you see up there. We have mobile facilities that have traveled around the world. We actually just recently decamped from Tasmania, Australia. Oh, yes, I got to go there. It was amazing. We also have just deployed a site to Arizona where we're studying dust storms and the North American monsoon. And we have a long-term, semi-long-term site, 5-year deployment to northern Alabama in Bankhead National Forest. Basically, wherever we have computer models that try to predict the future, try to predict what weather is happening next, whether it be the next day, the next week, the next decade, wherever we can see that these systems are struggling with predicting the future, we go and we take 2 measurements. One thing I want you to take home from today is AI is here. It's a really nice tool, but bad data, bad information equals bad AI. So our main job is to collect the information to make AI really good. Little bit of background. You might have noticed from the accent, I'm from the South, the very, very deep South. I got into physics when I was young. I was fascinated about the way things work. I was also a mad computer nerd. I don't know how it worked in the US, what technology you guys were seeing back there. I had a TSR-80, a Tandy computer. I got into BASIC. I learned how to program. I thought, that's it. I want to be an IT administrator, until I worked out I didn't want to be an IT administrator. But I did when I went to college, I fell in love with physics. Still was really into computer science. I then got into forecasting. I loved storms. I loved watching the way the atmosphere worked. And then I kind of realized that I needed a job. I became a weather forecaster for a while at the Australian Bureau of Meteorology, which is like your National Weather Service. Followed my wife to Melbourne, Australia, and joined it there until one day someone noticed I was playing around with weather radars and said, we just bought a bunch of weather radars here for science in Australia, in the United States. And I said to my wife, Chicago, that sounds like fun. So that's why we're here now. Gillian, should we go on to the next? We're going to do some Q&A.
Yes. I'm going to come back around. All right. Well, I'm going to have you start out with this, because when we were talking today, you were talking about different modalities for AI. So AI isn't one size fits all. It's not, just throw it in AI. We say that kind of generically, but there are a lot of different, I'm going to say flavors of it, because I was admiring cheese trays. So tell us about those flavors.
That's a really good question, Gillian. First of all, let's zoom out a little bit and talk about what is AI. AI is a series of computer science-based technologies that mimics human behaviors. It's anything that can take something you see, either ascribe a pattern or predict what's next. That can be anything from, I don't know how many people have a mathematical background, but putting a couple of points on a chart, drawing a straight line through them and going, if I have point A, point B, and point C, and I draw a straight line, point D should be what's next. That, as boring as it sounds, is artificial intelligence. You've gotten certain points. You've built a model, which is a straight line. You've gone, if this was here right now, here then in the future, I expect it to be here then in the far future. That still is artificial intelligence. Underneath that broad umbrella of being able to mimic the human behavior of predictability, we have a whole gamut of different technologies under that. You've got machine learning, you've got computer vision, you've got expert systems, you've got agent-based modeling, you've got large language models like ChatGPT, Claude, and all of those things. That's kind of how we're going out to the extreme end. In terms of scientists using AI, as Gillian was saying, we've kind of 3 modalities here. We have, you were talking about the way in which a tokenized model can predict the next word. The cool thing is that based on decades of weather observations, an AI model can take the current state of the atmosphere, looking at everything that has happened before. The temperature in Chicago was this, the temperature in Duluth was this, so on and so forth. It can predict the next state. So that is one huge area that AI is impacting our science. These neural network-based predictors of the future state of the atmosphere. There are pros and cons to this. The huge pro is it's really fast. If you have a normal weather model that Tom Skilling and everyone uses to predict what the weather is going to be. We get our observations in at 12 UTC, which is about 7 a.m. in the morning here in Chicago. That all comes in through the weather network that spans the globe, comes into Silver Springs in Maryland. They will then take that, they'll make a pattern match to the whole world, make a weather map and go, what's actually happening? They'll take a bunch of physics, bunch of huge lines of computer code, like millions of lines. And then it takes about an hour. So it comes in at 7 and by 8, we've got our prediction for the next week. A AI-based model can do it in about 10 seconds. The con, we have no idea how it does it. So when it goes wrong, we have no idea why it goes wrong because there are no physics involved. Basically, an AI model is pattern matching, like Gillian showed before with the cat, so on and so forth. It's going, there is this blob there. I know it moves at this speed. That could be a hurricane. It could be a derecho, could be a tornado. And it moves it the way it's always gone. Why it went there? We've got no idea. The second modality is pattern matching, exactly what I said before. Again, I'm a bench trained meteorologist. When I went through my training, it was a bunch of, we're going to put you in these displaced real-time scenarios. You're forecasting tornadoes right now. You're going to be putting out the tornado warnings. You look at radar imagery, there is a particular shape to a storm. There's a particular pattern and a particular way it evolves, the way it moves. You'll kind of go, I want to put a warning out for this storm. AI is really good at predicting those patterns. Again, as long as we use it responsibly and there's a human in the loop checking it. The third one is exactly what those of you who raise your hands are doing. Yesterday, actually, the day before yesterday, I got a hint there was going to be a smoke event over Chicago. I saw in the forecast, my various social media channels were going up. I went, oh, I should keep an eye on this. And what did I do? I asked Claude. I said to Claude, which is one of the agents that I use, I said, I really want to make some really nice plots. I want to make some graphics that shows from EPA sites across the Midwest how much smoke do we have in the air? So I asked Claude, put together this wonderful plot, and that showed all these stations across the Midwest. And even this morning, and we'll show you this graphic later on, I asked Claude, I said, how unusual is this? And it showed me this really nice data source that I could then work out that, yes, this smoke event we had over Chicago is one of the worst we've seen in history. So just like you all, as scientists, we use some of these AI agents to help us discover new sources of knowledge. And just almost like, when I was growing up, I grew up and went to college in 1999. So this was at the birth of the internet. I learned how to use Netscape, Alta Vista, and all those things. And then I learned how to Google. So learning how to use an agent right now is learning how to Google. And that's kind of one of the new skills we're going to learn. So.
All right. Yes. So one of the things that you've said and that some of your other scientists have said is that with AI models, as with weather models, garbage in is garbage out. So I want you to talk a little bit about some of the ways you are working to get good observations, good stuff in, good stuff out.
That's a really good question. So we artificially, as atmosphere, put ourselves in different boxes. I'm an observation scientist. I generally don't use models that much. I work with people who use models, but I like taking new measurements of the atmosphere. When we train an AI, or even when we get new physics, new lines of code into a simulation, we call it the word model. And when I did my communicating science course, one of the things they told me was that careful with the use of the word model, because people have all different ideas of what the word model means. This is not someone who walks up and down the catwalk. This is something we use to predict the future. It's something we use to put in a state of the atmosphere times 0 and work out how it progresses. Now, when we run a model, it takes various physical ideas of the way the atmosphere works, the way air moves, the way clouds form, the way rain works, the way dust moves, the way wildfires happen and the smoke comes down from our north. And so a physics-based model will take all our observations and our knowledge of the atmosphere and work out what happens going after, with lines of code, including various physical constants, such as how much heat is released when precipitation falls out of a cloud. An AI model will take what has happened before. So in both cases, it's vital that we take measurements where it matters. And so through projects like Crocus, which was a project we had funded by the United States Department of Energy, run out of Argonne, we took measurements deep in Chicago. Your average long-term model that predicts decadal change, the size of the pixel, you imagine take a picture with your camera, right? You zoom right in, we've got pixels, so my face is broken down into different colors. Our models, our simulations of the atmosphere, whether they be what Tom uses for tomorrow or what we're interested in for the next decade, you zoom in, they're broken down into pixels. For the long-term models, they're about, what's 35 kilometers? Let's call that 20 miles. You take a 20-mile block, you put it over Chicago, it's all the same. The average height of buildings over Chicago, it's like 10 meters. So it's really important we get deep down in the urban canyons like you see here, and we understand how the air flows through that. Because when we have heat wave events, I don't know, wildfire smoke events, it's absolutely vital that we take measurements deep in these urban canyons, including using lasers. We do shoot clouds with lasers. It's really cool. Towers like this, where we actually measure how you get water and carbon dioxide and methane exchanged from the surface into the atmosphere, and through various other instruments, including getting students to go right down the urban canyon to work out, when we have a heat wave, how does the heat vary from block to block, neighborhood to neighborhood, so that we can actually build better models, better computer representations of the atmosphere. So whether it be through our slow physics-based mechanism or our very fast AI-based mechanism, it's fed with the right data, but also when it makes a prediction, we can work out, is this out to lunch or is it correct? So.
Do you want to say anything else?
I can say,
Okay.
This is the really so, by the way, let's just appreciate the change when we're deploying in Humboldt Park in February. We actually had to wait for the ground to freeze because we needed to get a cherry picker, a boom lift. I know, is cherry picker an Australianism? It's probably an Australianism.
That's what they call it.
Yeah. So we had to actually put this boom up in Humboldt Park. And you can see my colleague here, Joe O'Brien, absolutely freezing in the middle of summer, trying to put up our tower here. Literally before a tornado came really close to UIC here. So we've actually deployed instruments across Chicago in all seasons. And one of the things I want you to take home from this is really the way in which the city modifies the way our weather works here. How many times have you heard cooler by the lake? Chicago, we are unique. We are a city by the lake. So we go from lake to mega city to the rural urban gradient to farmland. I collaborate a lot with NIU and I am a joint appointee with UIUC. The speed at which we go to skyscrapers to cornfields is nuts here, and it is not represented in any simulation we run. This is where the frontier is really representing the city, the cornfields, the lake, taking more measurements over the lake so that we're able to gain a better predictive understanding of our environment. And again, the real frontier is getting beyond that 7-day forecast. I can't tell you what the weather is going to be in 10 days. Our goal is to be able to give probabilities to understand when we're going to enter a drought or enter an area where we might get flash floods. For the Intermountain West, when we are going to be in a fire-prone region versus a non-fire-prone region, it's really giving some of our decision makers an earlier heads up, like, yeah, you all should be getting ready for this. It is absolutely crazy to me that last 2025, we were in a region of drought. We were dealing with haboobs and dust. Who remembers the haboob here? Some of us remember the haboob. We had this huge dust. Sorry, a haboob is a big dust storm. I believe it was in late May, early June. We had that huge dust storm come across. That was because we were in a region of drought, and there was a thunderstorm that dropped a huge blast of air that sent a massive dust storm over the Chicago region. Now we're in a region of flood, and all of a sudden we have folks downstate with flash flood warnings, things like that. So it's only from sub-season to decadal period here. What have we got next?
All right. So we are at the Chicago Maritime Museum. So I want to talk about weather. Yeah, Maritime. Yeah, I want to talk about. I thought everybody would cheer them. It's okay. Yes. Yeah. Go boats. Okay. So weather and maritime history. So as you know, Scott, Chicago has a rich maritime history, but it also has a tragic history of shipwrecks. So I want to talk a little bit about how the lake influences the city, how the city influences the lake, and how both of those things influence shipwrecks. So we're going to start with the Lady Elgin, 1860.
Perfect. Let's give a little bit of background first about why Chicago, why the Great Lakes, and why we have this history of shipwrecks. There are a variety of different storm systems that affect the Chicago area. You've got clippers in the winter. You've got what is it called, like a witch storm, which is they noted during the Edmund Fitzgerald. So the lake has a unique influence over our weather. It can be both a source of calming storm systems as they come across when it is cool in summer. Often in summer, when the lake is still cool and we have these spring storms, you'll see a great big whopping supercell heading towards Chicago. And all of a sudden it just dies before it hits the lake because there's cooler air around there. Thunderstorms need three things to survive. They need something to get them going. That could be a cold front, it could be a lake breeze. They need a lot of moisture. They love moisture. The wetter it is, the corn sweats, they love that kind of stuff. And then what they need is for the air to be unstable. What that means is cold air above, warm air down below. We get that in autumn and we get it in spades in spring when there's still wintertime air above and we're getting Gulf air from the Gulf of Mexico up below. So the lake adds an extra ingredient that's particularly in the spring. It's warm. And when we have a cold air mass coming down from the north, coming across warm lake air, it can cause a bomb cyclone. And a bomb cyclone is a storm system that will head over the lake, feed off that warm moisture from the lake and really get radically intensified. The difference between the Lady Elgin and Edmund Fitzgerald was the invention of the telegraph. The telegraph had just been invented before the Lady Elgin. I think it was like 1940 or something like that. The telegraph is key to our ability to get forecast the weather. Because what happened with the telegraph was someone out to our west would say, hey, Scott, I'm in Davenport, Iowa. We just had this beast of a storm come through. You in Chicago, looked like it was going about 20 miles an hour. You're probably going to get it sometime tonight or tomorrow. That was like actually the second epoch of forecasting. The first epoch was the weather today. will probably be the weather of tomorrow. The second epoch was what happened downstream of me will actually hit me later on. That's where our first weather maps came from, was a bunch of folks across the United States of America calling in the weather. Some folks actually in Washington, D.C. at the Smithsonian actually trying to make a map of that. And where are these systems? Now make a picture. Now draw lines between equal lines of pressure. They denote where the weather systems are, and they'll literally look at from one day to another. They go flip, 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 flip between it. I even did that when I was in med school. We still did that. You draw weather systems, so flip between it to see the animation, see the propagation of the storm system. Problem was, they made a weather map for Lady Elgin. The room burned down. So we do not have a weather map for when the Lady Elgin went down. Edmund Fitzgerald, however, we've got a weather map. Because this was quite a few years later.
1975.
1975. And we can actually see this low pressure system here sitting over north of Green Bay here. And what that's doing, it's actually sending winds way down. So the winds are actually going around this low pressure system and heading down the lake there. And it's actually that fetch down the lake. So one of the things we look for, and many, many years ago, I did high seas forecasts back at the Bureau of Meteorology in Australia. One of my first jobs when I got out of med school was to do these high sea forecasts. And you always look at fetch. It's the length of a line of constant pressure down a lake, and it's the gradient between that 984 hectopascals and 992 there that means that that's going to squeeze the air and push it down the lake. I had the pleasure when I was at the Bureau we actually worked with the Brighton Yacht Club. They took us out on their boats, showed us around, because the maritime industry, the amateur races and the professional races like the Mackinac boat race here, they are big consumers of some of our forecasts. Wind speed and direction, sea state, the height of waves, including the chop and swell, was a huge thing that we did. So not just the predominant direction of the waves, but the way the chop would come across the swell was a big thing they were looking for. And one of the hugest challenges here was that fetch down the lake, which is, I can't remember what the name of the height of the waves were, but that's what led to the sinking of the Edmund Fitzgerald. But the real difference was we now have these weather maps. So we see all these individual observations across the United States that actually allow us to place where these weather systems were. And again, the real technology was the invention of the telegraph and then the international telecommunications network that led to the internet and now leads us to be able to make the maps we can make today.
And I want to point out one more important moment in maritime history that also led to modern meteorology. Tell me a little bit about World War II in meteorology.
Yeah, so the most important
A little bit.
What was the saying? They had a better army, but we had better weather forecasters. Yes, the D-Day landings where we had those storms over the Atlantic was a key moment for the success of modern meteorology. The ability to now forecast for the D-Day landings so that those shallow landing boats weren't sinking was key. More importantly, it really led to modern weather forecasting and led to the investments we see today. The team that was involved with the under pressure movie you've seen were under budgeted, and there was a lack of investment in meteorology, and World War II really led to the renaissance of weather research that we see today, including flying ex-military aircraft through storms to understand how storms work, really using ex-military ships through a project called GATE, where we put all these ships out across the Pacific, and the Pacific is really the source of the weather that we have in the United States. We talked a bit about AI and data and about how your tokenized model predicting the next step. The next step for us is west. Our weather comes from the west. You keep going west, you've got the Atlantic. The Atlantic is a whole lot of water with a heck of a lot of nothing. And it's, guess what? It's not in the United States of America. either. So it's in our interest, and we are measuring across the Atlantic. And GATE was one of the big experiments that really improved our understanding of the Pacific. Wrong ocean.
It's only one ocean.
It is only one ocean. As an Australian, as an island in the ocean, we get that. This is really cool. This is actually from our colleagues at the Cooperative Institute for Scale Meteorology. This is actually a reconstruction of the satellite imagery over the United States from the Edmund Fitzgerald went down. And if you just hit that, there we go. So you can actually, there it is right there. That's actually the storm system there that actually led to the sinking there. It actually kind of came down from the Pacific, actually arched up over Midwest into the lakes there. The kind of cool thing about this is that when they used to receive satellite imagery back in 1975, it was all printed out. It actually came over basically again over a satellite link, but they did not digitize it. They printed it, and then recently, on the anniversary of it, they've actually gone back and digitized and geo-referenced all this imagery so folks can study it again.
Yes. Okay. So between 1975 and today, we've had some improvements, and one of them is AI, as we've been talking about. So how is AI and machine learning, how are they changing what you do?
So a variety of ways. One, they're greatly accelerating our ability to be able to make predictions when we make an AI-based model, AI-based simulation of the atmosphere that again takes what the atmosphere is doing now, trying to work out what's going to do later. These are very, very quick to run. So we're able to run it very quickly. We're able to run many different variants. What that means is that one of the uncertainties, one of the reasons why our 7-day forecast isn't always right is that we have a sparse observing network. We don't have observations of the atmosphere. We don't have balloons. We don't have planes. We don't have satellites. We don't have radars every meter. So where those observations are sparse, we know those regions lead to greater uncertainty. What exactly is the temperature, humidity, weather pattern in the tip of Argentina? What's happening down in Patagonia? We don't know. So what we can do is we go down to those areas and we can take the pattern that we have right now and we can call it perturbing. We can like add a little bit of noise down there, add a little bit of error. And then we run our model, our simulation, but rather than running it once, we run it 100 times and with slightly different patterns. So we go, if we make this little mistake down here, how does this mistake propagate to changes in our weather in Chicago? What if I got the temperature 1 degree wrong in the Cape of Good Hope? What difference does that make to Chicago? And one great thing about machine learning is because these models, rather than taking an hour to run in a supercomputer, I can run it in 10 meters on my laptop. I can do these massive ensembles. We call them ensembles. And that allows me to say that, you know what? I don't know what the weather is going to be in Chicago in 7 days, but I can tell you what the spread is. I can tell you there is very, very little chance, so little chance it's going to be 60 and clear. There's also very little chance it's going to be 120 and smoky, but I can give you an idea of that spread. That really helps decision makers. They like bounds, they like uncertainties, they like percentages. The other way, as I mentioned before, that it is really, really useful, it's really supercharging our ability to be able to ingest large amounts of data. The Atmospheric Radiation Measurement User Facility. By the way, I'm going to do a little segue. It's a really old name. We're 30 years into our 10-year mission, understanding how sunlight interacts with everything in our atmosphere. The code name, when they're out in Oklahoma, founding our first site, It's called the sunlight experiment because it was all about, you've got the sun, you see it up there. It comes through the atmosphere. It interacts with CO2, it interacts with ethane, it interacts with tiny smoke particles, it interacts with cloud droplets, rain droplets, and then it gets down to the surface of our planet. It hits cornfields, it hits tarmac, it hits city. They heat up. That yellow light that came in, it goes back out as infrared radiation. Radiation you can't see, but if you stand in front of your heater, you can feel it. And that's the way it goes. If you stand in a hot parking lot, you can feel it. That also interacts with smoke, with CO2, clouds as it goes back out. So the atmospheric radiation measurement user facility, we're all about cataloging everything sunlight and infrared radiation interacts with. And that is, I have lost my train of thought. Well, machine learning. So that is, yeah, that's yeah. So back to AI though.
Yeah.
So one of the things that we've been doing in ARM is actually taking all those components, building models. We call rapid radiation transfer models. They sit in every weather model you've got there and making that machine learning based because it's a lot faster to run. So,
All right. So
you got to keep me on track.
well, yeah, I'll just tackle you next time. So I know we want to get to our audience questions. I have one more question for you, and then I'm going to turn people loose. So we've talked a lot about AI as more of a passive partner, more of something that you give it something to do and it goes and does it. But what about AI as a partner? I like Star Wars, and I think about, the droids in Star Wars like C-3PO, or R2-D2, and you're like, go fix the hyperdrive, and they just go do it. Or they take measurements. So what do we have that's like that? How are we using, AI buddies? Are we throwing them into the lake and seeing if they swim and seeing what they find?
So a couple of things there. First, let me be very, very frank with you. We need to be very careful here because AI is not perfect. So within an Argonne National Laboratory, we're all about the responsible use of artificial intelligence. AI is based on our collective understanding and you've heard this term, hallucinate. It can join the dots in the wrong way. You've all seen, many of you have probably seen AI slop and things like that. So for us, it's all about how can we use AI responsibly in order to advance human knowledge. One of the other areas we're really interested in is actually bringing AI into the loop, which is this idea of autonomous laboratories. So day like today, we had some storms, we had some smoke haze. I work a lot with these things called weather radars. They involve an antenna. It looks like a dish, looks like a satellite dish. And we throw pulses of electromagnetic radiation there. It's very safe. It's very, very low energy. That will hit a cloud, tell us about what's in a cloud as it reflects off the cloud and comes back to me. So if the sky is clear, I might want to just put my radar upwards, try and work out what's happening in the atmosphere. If I can see a cloud, I might want to follow a cloud. If I see a wide storm system, I might want to image that storm system. Where AI is really useful is diagnosing what's the scene, what's happening here, and saying, hey, you drivable instrumentation that you don't set and forget, you have some choice in the loop. Maybe you want to be looking over there. Maybe you want to be looking here. So for the idea of autonomous laboratories, whether it's flying drones, whether it's steering antennas, whether it's pointing lasers the right area in the atmosphere, AI is extremely useful.
Okay. All right. I could ask questions all day, but you all came here to ask questions, and we have some folks online as well that might have questions. So let's open it up. Yes.
Yeah, you mentioned building models. Granularity of the data that you
Yes.
at any given point in time. Do you see that the building of models as being more efficient when you get better granularity both in time and space?
100%. So there's this technique we call a simulation. That is, if you have, like through Chicago, we go back, oh, this works here. Imagine I've taken a couple of tracks here, and here. We want to then build a map, like building a
Can you
piece
come
map.
back to this side so people online can hear you too?
Sorry, people online. You'd have to all imagine me pointing at that. When we take those points and we basically average them, we don't know what we're missing. So there's this real dance in our community, in the atmospheric sciences community, between those that take highly detailed observations and those that build these models, these simulations of the atmosphere. And it really is that they'll come up with something, they'll say, isn't this cool? We'll go and we'll take observations and say, you're kind of missing this here. So as we take more granular observations, and we are driven by those models, we'll often use those models, we'll run them over a city like Chicago and show how we actually need to take new observations because of failures, because we can see these forecast failures of these models. And some of the best studies are where we've actually used the model to identify here, here, and here is where we need to take these new observations. So there's this real interplay between the granularity of these models and of our observations. I'll give you some numbers and I'll work in kilometers briefly, and Gillian can help me convert these to miles. Our highest resolution operational model is 3.7 kilometers. Let's call that 2 miles.
Let's call that 2
So
miles.
imagine a postage stamp over Chicago. It's about 2 kilometers.
2 blocks.
Yeah, 2 blocks. Exactly right. Our highest resolution long-term decadal model is more like 30, 40 miles. So if you want to go beyond 10 years. So that's the challenge we have, is taking the city of Chicago and the measurements therein and representing that. We're just about to have a paper accepted really soon. Gillian's a co-author on a field campaign we did called Crocus Urban Canyons. We went right into Chicago and we launched 42 weather balloons, because a weather balloon gives you an atmospheric sensor, temperature, humidity, wind speed on the bottom of the balloon. And that doesn't just give you what the weather is at the surface, it actually gives you a profile in the atmosphere. So back in your previous slide, what this teaches us is about, oh, there it was, about how temperature and humidity varies with height. And then you can do the balloon now, and how the city influences that. No one's done that before. So that is a unique measurement, particularly in Chicago, that can help us build better simulations of the future. So, yes.
My question was, which AI agent do you find, or agents you find most useful for your work? I heard you mention Claude. I know there are about 7 or 8 out there.
So this is my opinion, not the opinion of the United States Department. Claude by a country mile. Claude science, game changing, 100. And I ran a poll internally at my at Argonne. So they all have different characters. Claude is a scientist, was it ChatGPT is an artist. So if I need to make a logo or I need to make a diagram, I use ChatGPT. If I want to work out a scientific workflow, I use Claude.
So an interesting add-on to that is that, Claude might be good for some things, but there are other things that we need to create
Yes.
our own models for. And so that's
100%.
another thing that we're working on is like,
And that's a really good point. So you have all these agents right now. And I always like to say these are agents that have kind of come out of high school. So one thing we do both within the atmospheric radiation measurement user facility, but also at Argonne, is we retrain a lot of these agents. We'll basically put them through university. I can't remember what the acronym stands for, but they're called RAG pipelines, where basically you take the structure of the agent and then you expose it to either papers, data sets, or information that like ARM has collected or ALCF has collected, and that makes them a lot more useful. Basically kind of retrains them to be experts in our field rather than just being generalists in multiple fields.
Yeah, so this would be
Yeah.
for cancer, for,
Exactly.
human health, for batteries, energy storage, so different models for different things, specially trained.
There's a tool called Boodlebot. It'll actually choose the best
Yeah.
tool for the question.
Boodlebot, for the folks online, is a tool that trains models to be better, or picks the right, points your question to the right model.
Thank you very much.
Say it into the mic.
Retrieval, augmentation, generation.
We talking about fact gathering and putting together things, but it isn't really, you're the intelligence.
Correct. Kind of answer your question, I'll give you an anecdote. So again, I have begun using AI when I want to build something. So whenever I author it, I'll often use the word co-designed. So it is the way I use agentic AI is as a co-pilot. I am completely saying, I'll give you an example, which is, weather radars. We've got these really cool weather radars that can measure the shapes of drops. And these dual pole radars, they will measure the shape of the drop horizontal to the earth, and they'll measure the shape of the drop vertical to the earth. And drops, when they fall, they look like hamburger buns. They kind of get squashed. They do not look like teardrops. And so I wanted to analyze areas in a radar image over, don't ask me why, I can tell you over a beer later why, in Serbia, in Europe. And I wanted to work out areas where these drops would be really, really circular, because I wanted to calibrate the radar. So I gave Claude the broad ideas, and I said, I want you to look at this and perform this kind of analysis, and just give me the code, because I didn't want to write the code. It could write the code for me. I gave it all the science. It basically used what it's seen online to put that code together. So it's not reasoning at all. It is taking broad guidance and finding pattern matches and presenting it to you as the scientist, saying, is this the kind of code you're looking for? So, however, boy, does it get it wrong. And it gets it wrong in weird ways. Normally it's in terms of something like the way something is named, the way there are various norms that it hasn't learned yet. It is getting really good. And when I was way beyond when I was growing up, when I was really kind of going through grad school, it was all about learning how to Google. And so learning how to use some of these agents is kind of learning how to do a good literature search. Checking your references, making sure that it is scientifically robust, contextualizing it is really important. And I do believe one of the future graduate courses we're going to see, or undergraduate, is like prompt engineering. Students are going to need to learn how to write good prompts and how to question the output of these various agentic AI systems.
And do you just want to explain what a prompt is briefly?
I do. Oh, sorry. That's a really good question. So when we Google, you'll go to Google and you'll say, what is the capital of Moldova, or something like that. Prompt engineering is where you know a little about the AI, and I might say to the AI, here is, I'll take a radar image. I'll take a picture from the National Weather Service, and I will give it to the AI agent. I'll say, imagine you're a meteorologist. Would you classify this storm as a supercell, which is a type of storm that is really destructive, a low precipitation rain system, or would you classify it as no weather at all? So prompt engineering is thinking about the way the agent works and working out what you need to ask it to get its answer. A great example of this, we have a little project, it's called LLM Assisted LARS, radar scenes, LARS, LLM assisted radar scenes, run by my colleague Bobby Jackson, who lives in Bridgeport here. And so you ask an agent, tell me what the storm is. For each storm, you'll get a completely different answer. It might say, but if we say to the agent, do you see a tornado in this storm? You'll only get yes or no. So the great thing about that is I can now give it the NextRad network, which is one of the jewels in the crown of the United States weather enterprise. We have 150 radars, weather radars across the United States that have been running since 1988. So that is, I think we're on 10 petabytes of data, which is on order about 150,000 feature-length films. So trying to build statistics of how many tornadoes happened across the United States. A human can't do that. So we can train a large language model and build really well-engineered prompts so that we don't just get some random description of the weather for each radar image. We say, do you see, imagine you're a meteorologist. Do you see a tornado in this image? And here's the crazy thing. This is actually something, I'm going to give you some breaking news here. This is something we just discovered last week. So when I make radar images, when I take a picture of the weather from a radar, I like to use what's called colorblind friendly color maps. These are color maps. These are presentations like you might see on WGN or something like that, that folks who have red-green issues in viewing, they can actually see well. That's fantastic for the community because it means 9% of men and 1% of females who are colorblind, who have issues with, who have color vision deficiency can see them. So we started using that in our LLM to classify situations. It was terrible. It did an absolutely horrible job. You want to know why? Because all of the internet's knowledge was based on the classical color maps, because all of the radar imagery that was online was based on color maps that mapped radar imagery to intensity that was based on a color map that was developed by the National Weather Service, which is a terrible color map. But as soon as we changed the agent and said, okay, I'm now going to give you this particular spectrum of colors, it all of a sudden it worked really, really well. So that is, it's a lesson learned, but it's also a terrible thing. And it just shows that these AI systems, it's so much based on what the data we train it on.
Yes, absolutely.
That was a long answer.
That was a long answer, but that's okay. Nobody left. We probably have some online questions as well.
Don't yet.
Oh, we don't. Okay.
I had a very unusual experience 2 days ago as I was planting some very small plants. I was like 6 inches from the ground. It was a broiling hot day and I felt a cool breeze way down. And it reminds me of when I have been diving and taken away by the current. And to go back, I go down to the
Yes.
because there's a reverse current. Is this related?
100%. Absolutely. We have this thing, it's called the boundary layer. It is the layer of air that connects us on the planet to the broader circulations of the planet. And the closer you get to the surface, the greater the influence tall structures, then trees, then low plants have. In oceanic science, it's called the Ekman spiral. As the deeper you go, the winds actually change direction as you go down. Same thing where we are. So the closer you get to the ground, the more influence it has, the cooler it is. It's especially if you're in a forested area.
There's lots of trees.
Exactly. But how it goes, so again, the wonderful thing about trees is that not only do they still the air, they also pull moisture from the soil, and they literally sweat it out. So trees have an amazing cooling effect, both through stilling the air, stopping those hot flows from the south, but also evaporating air. They pull moisture from the surface. When that moisture evaporates off the leaves, it actually cools the air down. It will also keep it a little bit warmer at night, so it's not a complete win-win. But that's kind of was part of the goals of Crocus, is to be able to quantify exactly the kind of effects you're talking about. Definitely.
Is that to hear about corn sweat?
Completely the same. It's and corn sweats, which we're really interested in. The corn sweats are so corn has a unique ability, a unique root structure, moisture from the Midwest thrown in the atmosphere. So if you look at the difference in moisture content in the atmosphere, it is like far greater downstate in Champaign and is up here because you're in those cornfields. It's thunderstorm fuel as well. And that actually is an active area of research we're doing right now. We are really interested in the role of managed ecosystems, soy, corn, and so forth in this massive gradient we have between Chicago, Iowa, and Nebraska, and what difference that makes to these. Who's heard of derechos here? So a derecho, massive type of thunderstorm, like one of the nastiest we can get out there. The word derecho is Latin for wall, literally a wall of storms. So back in 2020, August 8th, we had a derecho here that was, if it was a hurricane, it would be the third most expensive hurricane here. We're really interested in the role of like these managed ecosystems and these derecho systems.
Yeah, I the follow-up with what you said about the corn sweat, feel like the corn planting in the Mideast with the refinements in farming, we've seen like the density of corn planting increased by a threefold over the last decade or two. And because of that, the moisture in the air has been so much greater too. You used to be able to look up in the sky and see the Milky Way.
Mm-hmm.
And you can't right now because of the humidity. All of that humidity from the Midwest has exacerbated weather systems throughout the Midwest. You know, and we don't want to lose the time with the city of Chicago because when that weather comes to the city of Chicago, it does something else too. So there's a lot of stuff you can chew on right there. How much has this changed over the last couple of decades?
We don't know, which is exactly why we want to take these measurements. No, we do not know the role of these managed ecosystems. And we're talking about the models and AI before, they are not well represented in these. So the simple answer is we need to take more measurements. So that is our role at Argonne and other places, is to actually take these measurements, provide that information so folks can make better decisions. So yeah, definitely. More managed ecosystems mean more evapotranspiration.
And we have
up the back there.
Last question. I'm going to call.
Does this thing take into any account sun, solar flares, heating up, slowing down solar activity?
Absolutely, all the models we use look at the variability with solar cycles. It is a very small perturbation on top of some of the other cycles that we see. It's like roughly about 5% of other cycles, including other managed ecosystem issues as well. So absolutely.
Right. I think we'll hang out for a while
Yeah.
if you have more questions, but I just want to direct your attention to this slide. If there were things that you wanted to learn more about, feel free to take a picture. We also have these AI Roadshow postcards up here so you can see where we're going next. You can learn more about AI at Argonne, learn more about Scott and our other researchers. We will be at the Aurora Public Library on August 6th, talking about demystifying AI. And on August 29th, we will be at the International Museum for Surgical Science.
That is a really cool. So up near the Northwestern campus, it's, yeah.
Yeah, so definitely come up and keep asking questions and talking to us about AI, but thank you so much for your attention. Thank you. You're welcome.
Back to the slide with the links.
Yeah.
Read that one.
Oh, there you go. Oh, there are your cue buttons. Oh,
And we have stickers up here if you want stickers too. All right.
okay, wow.
Stickers. You, all three. Go for it.
This is my place to make a plug, but you know what you made me think of is Old Weather. Have you seen that website?
Which one, sorry?
Old Weather. So the British put up a website and they said, if you old timers know how to read cursive, Spencer script
Oh my God.
and round hand, they scanned all their ship captains, all those ship logs back several hundred years. And so what people like me will then transcribe the ship's log. They feed it into the AI and then they feed it into weather models to show how weather is, because the British Navy was all over the world. So that they have anchorages where they drop the anchor in every little cove in the world. And what's the first thing the master did? And they take the weather and they write it down. But the AI was having trouble reading the cursive and the old round and the round hand and the Victorian script. And so people were doing that. I'm sure the models have gotten better at doing that. But that's one way to longitudinally look at weather.
Those logs.
The ship.
I was talking about with the Elgin, that's we just don't have. With those weather records, it's really important to contextualize.
Yeah. This is just me, but I wouldn't name a sports team the Fire. You know, all the stuff that it ruined. I don't look fondly on the Chicago Fire. So why you would name a sports team the Fire? That baffles me. You should name it something positive, like, you know, it's in Chicago, great, yeah. That's very much.